morning all of you. Started with our part 2 syllabus yesterday. The dual nature of matter, the concept of photon with some details, and then the idea of de Broglie matter waves. De Broglie proposed the concept of matter waves, that is the duality of matter. Earlier it was a duality of light that was established. Light, which was supposed to be a wave, also shows the particle nature, and that is said light is dual. So radiation has a dual nature. Based on that, the point of nature loves symmetry. De Broglie proposes matter also associated with wave, and only those particles which are in motion will be associated with wave, the de Broglie wavelength. Yesterday we have explained the character of wavelength of de Broglie waves, all the different possible cases. Now, some 2 to 3 important points, conceptual points regarding our de Broglie wavelengths or de Broglie waves. One is, though the matter waves is proposed by de Broglie, the significance of matter waves is not explained by de Broglie. So the explanation of the significance was by Max Born, B-A-R-N, Born. Max Born calls these matter waves as probability waves. Matter waves are probability waves, which shows graph is always a representation of variation with respect to another quantity. Now here, probability of finding the location of a particle in space, and that is what is the significance of matter waves. And the latter, now supposing if we take up the case of matter, one important point I would like to tell you. Matter waves do exist for every moving particle, yes, no doubt, but remember, the wavelength is inversely proportional to momentum. Yesterday's result, lambda is equal to h by p, and the h value we know the 10 power minus 34 order. Minus 34 orders are there. Therefore, lambda is very small if the denominator term is in the normal things like ordinary bodies like 1 kg, 100 grams, bus, van. For all these things, the denominator term p will be very high. And because of that reason, the lambda associated with all these waves cannot be calculated. Whereas, if we consider particles such as electron, alpha particle, proton, which we call subatomic particles. For these subatomic particles, masses are very small, of the order of 10 power minus 27. Now remember, minus 34 in the numerator. To counter that, the denominator should also be as low as possible, and because of this subatomic particles mass happening to be too small, then those lambdas can be practically observed. So that is what is the case. So why wavelengths or de Broglie waves associated with ordinary celestial bodies cannot be observed? Because of lambda is too small and it is beyond our detection. We cannot detect, we don't have such instrumentation. Whereas for subatomic particles, lambda is in the measurable, detectable range. And now that is what is done by Davidson and Germer. It is an electron diffraction experiment which verifies the existence of matter waves. So remember, the experiment that verifies the existence of matter waves is, name is of course Davidson-Germer experiment, or one more experiment which we call GP-Thomson experiment. Two different experiments. Both are nothing but electron diffraction experiment. See, electron is a particle according to us. So particle and diffraction is a wave character. So particle definitely cannot exhibit diffraction. Now suppose if it is shown that electron is producing a diffraction pattern. What does it mean? Electron a particle cannot produce a diffraction pattern, therefore the diffraction pattern should be with the wave associated with the electron. So that is what is the basis of electron diffraction experiments. Beyond this we don't go into further details. So electron diffraction experiment, G.T. Thomson experiment, very fine. And now remember that expression which we will use in the Davidson general experiment. Yesterday we have told that charged particle accelerated through a potential difference, the electric field, lambda is given by, we have given this expression, lambda is equal to h upon, this is h upon under root of 2m vq, we have given this expression, you remember. And for electron we have given the case of lambda for electron is yes, it is 12.26 upon root capital V angstroms we said. In the Davidson general experiment, this for V is equal to 54 volts. This is for V is equal to 54 volts. The diffraction maximum is obtained. Substituting this value, you will nearly get it as 1.63 angstroms, which is detectable. We have such instruments, right? 1.63 angstroms. And this value, according to de Broglie equation, fits into the electron diffraction formula, the diffraction formula, which is 2d sin theta is equal to n lambda. So that is how the existence is verified. You remember this expression and this number. Maybe somewhere we will use this. Maybe this is a question in the board examination also. Right. One more thing is that when we say matter wave, another conceptual point to be remembered is Max Planck proposes that supposing if we take a particle like electron, the wave will be with a slight distortion. We will see it as a wave pockets. What is now that wave pocket? Now see here, wave pocket. We are mentioning it as wave pocket. If it is, if this is what is the case, which we call the wave, Now it is not what it looks like for the case of subatomic particles, but rather it will be, this is what is the structure that this is the pattern that is what is observed. Now this is what is referred as, of course as I have told you, these are probability waves, and this is what is called as wave packet, which is a spread of wavelengths over a central maximum, right? Therefore, for the case of de Broglie waves, instead of waves, we always consider them as wave pockets. And now because of this electron diffraction character, it is made use for a very big application such as electron microscope, which has really opened the doors for a lot of advancement in science and technology. We know that ordinary microscopes that we use, the compound microscopes or any other microscopes, they have their limitations, and the maximum magnifications can be like 200 to 500, not beyond that. But in the case of electron microscope, which works on the principle of electron diffraction, yes, the order of magnification is unbelievably huge. It is 10 rise 5 orders. So even the so-called very minute microorganisms can also be seen with greater details. That is what is the advantage of electron microscope, which is based on the principle of the dual nature of matter. So these things regarding the dual nature of matter. Now let us come to another second topic, that is photoelectric effects. Simple and definite question. There is only one and one equation which we will now discuss. Apart from that, few characteristics. Easy topic, easy scoring topic. Now get ready for the topic. Right, photoelectric effects. Very important topic. Now there are few methods in which metal surfaces surfaces eject electrons. Apart from photoelectric effect, in general I am telling you, metal surfaces do eject electrons under circumstances. One such is called as thermionic emission. That is, when metals are heated to very high temperatures, electrons are ejected. And the number of electrons that are ejected depends upon temperature of the metal surface. This is what is thermionic emission. Second one is what is called as one more case of field emission. Under the intense electric field, metal surfaces do eject electrons. This is field emission. Now, we comes to our present topic, which is photoelectric emission. This is also the case of metal surfaces ejecting electrons, but not depending upon the temperatures or not depending upon any external electric fields. What is that? Now we shall get into the details. Photoelectric effect, metal surfaces ejecting electrons. Now let us come one after the other. About 7 to 10 points now I am discussing. Each and every line, each and every statement is a solution for your CET NEET question. If not for JEE, for CET NEET, do remember each and every statement. First comes suitable radiation. Yes, for a metal to eject electrons, metal surface to eject electrons, it requires suitable radiation. In the case of this suitable radiation, we have defined three important parameters, right? First one is threshold frequency. Suitable radiation, when it comes, first point to be remembered is threshold frequency. Let me show with the symbol F0 I am suppose writing. What is this threshold frequency? Again an important conceptual question that appears. It is the minimum frequency. Remember, here these adjectives are very important. The minimum frequency above which photoelectric effect takes place. If frequency is greater than that particular value, then photoelectric emission will take place. Minimum above which takes place. Maximum frequency below which, if I say, below which I can say, then it is does not show photo emission. So it can be a kind of English sentences important in identifying the right option. Right? I am telling in terms of minimum frequency above which photo emission takes place. Now this frequency will correspond to a wavelength, therefore that is also now written threshold wavelength. Threshold wavelength, and I am using this symbol lambda O, lambda naught. Now since we know lambda, the wavelength is always inversely related to frequency. If I call it the minimum frequency above which photo emission takes place, this is maximum wavelength, because minimum frequency corresponds to maximum wavelength. Maximum wavelength below which photoelectric effect takes place. So this is how English becomes very important. F0, lambda naught. And since yesterday we have mentioned that radiation in the form of photons, with this frequency or wavelength term, now we define what is called as work function. Another very big definition. Work function using the symbol W. Since it is the minimum frequency, this corresponds to the minimum energy of radiation. Minimum energy required for a metal to initiate photoelectric effect. To initiate photoelectric effect, it requires minimum frequency or a maximum wavelength or a minimum energy. These two, F0 and W, we call it as minimum, and lambda naught we call it maximum. Therefore, let us use our idea of photon yesterday. Then W, what will be the expression? A big expression, 1 mark, regular for your examination. Lambda is equal to HF0. This is what is HC, bomb. Lambda naught, all in SI units we get in joules. The same given in the convenient units and practical units, it becomes electron volt. Then this becomes by small e the charge of electron, and therefore it is 12,400 by lambda naught. And of course I have told you, when we are using this, we straight away get the answer in electron volt. We get the answer in electron volt, provided lambda naught must be in angstroms. So this is first character of our photoelectric effect. It requires suitable radiation, and under that concept, the definitions and an important expression. Now comes another concept in photoelectric effect, which are photoelectrons. When metal surface is now ejecting electrons, now we are calling them as photoelectrons, because light, the incidence of light is causing the ejection of electrons. Those electrons are given the special name of photoelectrons. Now let us write the characteristics of these photoelectrons. First one is, photoelectrons possess kinetic energy. Photoelectrons possess kinetic energy such that there is a speciality in that, such that this kinetic energy, such that it ranges from 0 to a maximum. Whenever we consider a metal surface, a suitable radiation of course incident, then photoelectrons are ejected. Large number of photoelectrons will be ejected. Now in this large number of photoelectrons by the same surface, all the photoelectrons do not possess same kinetic energy. An important character, important statement for a question, conceptual question. The kinetic energy of photoelectrons ranges from 0 to a maximum. Why is 0 to maximum? Yes, it will be explained by Einstein using the quantum theory. So now, next point, another important point we are now writing, such that the kinetic energy, in fact, maximum kinetic energy of photoelectrons. Remember, this statement is a very big statement. Maximum kinetic energy of photoelectrons depends only on frequency of incident radiation. Only is an important term, and no only depends on, yes, let me tell two things: frequency of radiation and nature of emitter, the metal which is emitting, which we are calling as emitter. So two things it depends. Maximum kinetic energy of photoelectrons depends on frequency of radiation and the nature of emitter. Now for a given emitter we can say the maximum kinetic energy depends only on frequency. So these are some critical things about English when we read the question. If it is maximum kinetic energy of photoelectrons alone, then definitely both frequency of radiation, of course that frequency greater than threshold frequency, and also depends upon nature of emitter. Why all these things? Each and every character that now we give a statement will be explained by Einstein's photoelectric equation in our next stage. So maximum kinetic energy depends only. It means that the maximum kinetic energy does not depend on the intensity of radiation. Does not depend on intensity of radiation. Now, next one. Due to these photoelectrons, if they constitutes a current which we call photocurrent. So photoelectrons gives rise to photocurrent. Photocurrent, another important statement, see here. Photocurrent, of course, our definition is always I is equal to N by T times E. This N by T is the rate of emission of photoelectrons, E the charge of electron. This is what is photocurrent. Now, this photocurrent, when we consider, it is always saturated photocurrent. saturated photocurrent which is independent of emitter collector voltage. We can't get into all those details because we have an experiment, Hedge experiment, which is discussed in detail in the classroom. It is in the notebook. Go through one more time. Saturated photocurrent. Whenever we say photocurrent, we always mean saturated photocurrent, remember. Therefore, this saturated photocurrent, that is photocurrent, it is independent of, I am telling you, it is independent of, does not depend on, number one, frequency of radiation. Frequency of radiation. Though frequency is greater than threshold frequency and then we change the frequency, photocurrent, it does not change frequency independent. Number two, it also does not depend on, yes, nature of emitter, does not depend on nature of emitter also. Now, when I said it is independent of frequency, it also independent of wavelength, you should understand, because both are reciprocal. If it depends on frequency, definitely it depends on wavelength also, such that those results will be inversely related, right? Reciprocal results we will have there. Now, we say photocurrent depends only on, see now comes, depends only on, yes, intensity of radiation. Intensity of radiation. Can you make out that important things when you see it as a comparative thing? When we said about the maximum kinetic energy of photoelectrons, we said it is independent of intensity, depends on frequency and also nature of the emitter. Here we see an exactly opposite statement. Independent of frequency of the radiation incident and the nature of the emitter, but depends on the intensity of radiation. It can also be a kind of conceptual question, remember. According to wave, the definition of intensity is different from that of wave. There it is energy per unit area per unit time. Here we refer to number of photons incident per unit area per unit time. And when it comes the question of photocurrent, more photocurrent because of more number of photons that are incident, more number of electrons that are ejecting. That will be explained by Einstein photoelectric theory. Now do remember this as a conceptual thing. Now let me also give here one more statement. The photocurrent depends on intensity was my statement, right? Now let me say one very important equation, and it's a very important problem as well for the exam. This photocurrent small I proportional to intensity of radiation that is incident, capital I. Symbols, no confusion, small I for photocurrent and capital I for intensity of radiation, proportionality. Now, how to change the intensity? It is different cases. Bulbs can of different wattages used. Suppose I do experiment with 50 watt and then bulb is replaced by 100 watt and then bulb replaced by 200 watt. The intensity is changing. Yes. But other way of changing intensity is by changing the distance of the source of radiation from the emitter. So in the given examples of photoelectric effect, what is the terminology that comes? The distance of source from emitter. This distance versus intensity result is very much clear in our optics discussion. I proportional to 1 by small r square. So it is again inverse square relation of distance and intensity. Combining these two, the result is I proportional to 1 by r square. Therefore, this is I1 by I2 is R2 by R1 square. Again, what is the keywords? Distance of the source from the emitter, change of distance, photocurrents. Then the result is I proportional to 1 by r square. As usual, 1 for given values, known values, 2 for final values, unknown values. That is what we make use. So this is about photoelectrons. First one is about the photoelectrons possessing kinetic energy, and then the concept of photo current. Now comes another very important point regarding the photoelectrons, that will be in the case of experiment, which we call stopping potential. Now let us see the concept of understand all these definitions and concepts from the observations of Hertz experiment, which we have dealt in the classroom. Here we cannot do it in the crash program. So that is why giving you the statement and expression only. Go through your notebook, class notebook one more time. Stopping potential, we define it as the minimum negative potential. Remember, minimum negative potential applied to collector, because in all the experiments of photoelectric effect we have the emitter, which is the metal which is ejecting the photoelectrons, and then they are received by another agency, that is what is called as collector, and emitter collector potential difference will be maintained such that always collector is at higher positive potential, emitter is at negative potential. Now what is this idea of stopping potential, which will be helpful for us to know the maximum kinetic energy of photoelectrons? We give now negative potential to collector. Generally collector is given positive potential. Only to find out the stopping potential, we give negative potential to the collector. The minimum, again you see this thing, minimum negative potential applied to collector to stop fastest photoelectron reaching it means the collector. We said that whenever the photoelectrons are there, 0 to maximum kinetic energy, those electrons with maximum kinetic energy, fastest electron I have referred, to stop that fastest electron reaching the collector, the negative potential is given. Electrons stop reaching the collector means photo current becomes 0. Therefore, I can also say the minimum negative potential applied to the collector to make photo current 0 in the circuits. Now, this V0, the stopping potential, is a measure of maximum kinetic energy of photoelectrons. Again, the concept of electrostatics. If V0, the symbol I am using it for stopping potential, the maximum kinetic energy. Now take the case of the idea of electrostatics. Whenever a charge through a potential difference, what is the kinetic energy either gained or lost? Charge times potential difference. Here electron, therefore it is E times VO, V0. This is what is the stopping potential. So maximum kinetic energy is equal to E V0. Very, very, very important for the problems. Therefore, if in case of velocity, we will write it as half mv square, right? M for mass of the electron. Of course, the numbers will be note everyone. 9 into 10 raised minus 31 kg is EV0. Therefore, V is equal to under root 2 EVO by M. So another expression here, V refers to V maximum proportionate to V0. Again a relation, K proportionate to V0. Stopping potential doubled. What does meaning like that? So V maximum, K maximum are two more expressions to be remembered. Therefore, stopping potential is always a measure of maximum kinetic energy. One is given, the other one is asked. Such very simple examples you will see in your examinations. Now comes all important thing about Einstein's photoelectric equation. Einstein's photoelectric equation based on the quantum theory. In fact, it's a generalized quantum theory. Quantum theory is generalized by Einstein by saying that not only the emission but also the propagation of radiation and the interaction of the radiation is also in the form of photons. Now, this equation is based on two important statements. First one is that photoelectric effect is a one-to-one collision. Remember all these important terminology. One-to-one collision between whom is an important thing. It is one-to-one. One-to-one means one versus one. between incident photon on the metal with the incident photon with the electrons, which always of course refers to free electrons, with electrons present on the surface and also electrons present just below surface. So this is what is an important beginning. When photons incident, one photon interacts with one electron. Two photons cannot give their energy and interact with one photon. So it is always one photon, one electron collision. Second point is that the collisions will be taking place not only by the electrons on the surface, just below the surface also. These collisions are taking place such that the electrons present on the surface requires lesser energy for liberation, whereas the other electrons, when we say just below the surface, they require a bit more energy for liberation. And this is why, and that is why the case arises, the electrons which are now ejected from the surface, they will possess more kinetic energy or maximum kinetic energy, and it is when comes the question of below the surface, their kinetic energy will be lesser and lesser and lesser. So this is the first basis, and the second basis is that conservation of energy. Suppose I call these terminology. E, incident energy of the photon. E is the incident energy. It will be utilized in two ways. Utilized in two ways. First one is to free the electron. To free the electron from the surface, some amount of energy is required. And that is why the case arises of, earlier we have told what is that? Suitable radiation. If incident radiation is less than a particular value which we call work function, then electrons cannot be liberated and therefore no question of photo emission. Therefore, to free the electron, some energy is released, and that is what is referred to W, the work function. And the second one, remaining energy of photon. Remaining energy of photon imparts, IMPARTS, imparts kinetic energy for the photoelectron. So these are the two bases. This is nothing but conservation of energy. Now, this first part and second part now will explain each and every characteristic of photoelectric effect. Now let us take up this part, energy part of the concept, and give one important expression which is our need density problem. Let us see the conservation of energy part. E is equal to W plus K maximum. Now, writing it in 2 to 3 different forms, because already we have given the statements or expressions for them. Therefore, this is E. HF, F, the frequency of incident radiation, is H, F naught threshold frequency, and of course K maximum. Therefore, what is K maximum? K maximum is H times F minus F naught. Remember, we can also write it in terms of wavelengths. Then the same expression becomes HC 1 by lambda minus 1 by lambda naught. And of course, one more time I remind you, this F greater than F naught, incident frequency greater, minimum and above, and this lambda less than lambda naught, F greater than F naught. So this is what is K maximum, or whatever form that you would like to write. So different ways of representation of the same equation. Now let me take one more form, which is a very useful form, that form which is used to verify the Einstein's equation. Like, supposing if I take this, HF is equal to HF naught plus, see what is the maximum kinetic energy we have told? It is nothing but EV naught. This equation, I will just rewrite this equation as VO is equal to, yes, H by E times F minus h f naught by E. Is that okay? See, what is this? VO, the stopping potential, we are given in the form h by E times f minus h. Now you can see that this is in the form y is equal to mx minus c. This n here refers to the y equal to mx minus c is a straight line, we know that. M for slope of the graph and c for the intercept. That is, now if a graph is drawn between stopping potential and frequency of incident radiation, and supposing we show that it is a straight line and whose characteristics are m, the slope of the graph is h by E, and the intercept, when it comes to intercept, now let me draw the graph and show you. So this is how Einstein's equation is verified indirectly by drawing a graph between frequency of incident radiation and stopping potential. Now, what is this graph? Again, I am telling you, important conceptual questions and numerical questions from these equations. Now see, let us first show the graph. There are other graphs as well which I have not shown. I will do them as examples. Do remember, in photoelectric effects, number of times graphical questions are asked and we will do as examples. Now this is the frequency of incident radiation versus stopping potential. Because earlier we said stopping potential depends on frequency. Why? Because kinetic energy, maximum kinetic energy depends on frequency. Therefore stopping potential also depends on frequency. Maximum kinetic energy does not depend on intensity. Therefore stopping potential also does not depend on nature of, intensity of radiation. Now you see, this is one graph which is experimental graph. Experimental graph will be like this. So this is what is the graph that we get. Now supposing this graph is extrapolated backwards, extrapolating backwards, the same graph extrapolated backwards. Now we'll see two intercepts here. One is x-intercept, the other one is y-intercept. Now for this graph, three things which are probable questions for us is slope of the graph. Slope of the graph is h by E. Here you can find this h by E is the slope which is positive. So what will be the example, numerical example? You will be given the slope value and you will be given the value of E and asked you to find the value of h. We know h value is 6.6 into 10 raised to minus 34 joule second. But don't choose that as an answer, because in the experiment what is the slope that we get? Based on the magnitude we have to find the value of h. So that will be our right option. So slope is equal to h by E. One important tool. The second one is x-intercept. X-intercept will give us threshold frequency. When it is the question of threshold frequency, remember it depends upon the nature of emitter. And hence work function is also a characteristic of the emitter. Both threshold wavelength or frequency or work function, they are the characteristics of the emitter material. X-intercept is F naught. Therefore here, if the emitter changes, what happens? X-intercept changes. Remember, such that if this intercept is towards left, the shorter frequency, then its work function is lesser, threshold frequency is lesser, threshold wavelength is more. That is how we compare the things. Whereas when you look at this slope, slope is equal to h by E. It is h and E both are universal constant. Therefore slope is independent of emitter. Slope independent of emitter. X-intercept depends on emitter. Now what about y-intercept? What about y-intercept? This y-intercept is nothing but this value. See, this is what is the value of y. Therefore here it comes h f naught by E with negative sign, and that is why here this is negative sign, right? So this is what is the negative intercept. Negative y-intercept is h f naught by E. One more time you see, this is h, the universal constant, E, the universal constant, but f naught is again depending upon the nature of the emitter. Therefore, here also the y-intercept also changes. If the nature of, if the emitter is changed, x-intercept change, y-intercept change, but slope does not change. So these are the three important tools that we take from this graph. Right. Now, when we are ready with the characteristics of photoelectric effect, photoelectrons characteristics, and then all important Einstein's photoelectric equation, now our launch pad is ready for our numericals. Graphical representations, simple numericals, which will be continued in our next session. Have a good day.